Alright, we've come a long way. I think I've been doing this for like 3 hours now, but we can't stop now because we haven't gotten through the chapter. So let's see. Um, oh, I really like this question. No, there's one about the people racing each other. I think maybe that comes later. By the way, this is just a general pop culture thing that you should know about. Um, the relationship between Newton and Leibniz and the invention of calculus. That's something educated people know about, even if they don't know a lot of math. So you can read these books, or actually, Boyer is incredibly dry. I don't think this is a very good suggestion. This is an old man suggestion. If you want some good suggestions, then talk to me. I shouldn't be showing you this anyway because this is a copyright violation. Showing you the problems is bad enough. So I'm going to pause this and skip to the next section so I don't give away any of Stewart's textbook. So I know it may seem like every time we do something I say this is the most important thing. That's not really totally true. Is it? I don't know. But I kind of want to say it again about this, and I would argue that I'm not being inconsistent in saying that this is also the most important section. What's most important is to be able to do these integrals. There are other things that we'll do in class, but most of this class is about learning how to do these integrals. And there are certain skills involved in computing integrals that are only applicable to a few problems, and some of those techniques have to do with how to solve particular integrals that involve trig functions, how to solve particular integrals that involve rational functions, which are ratios of polynomials. And those are great to know, but they don't get you a long way. The substitution rule is the complete opposite for that. It's really hard to find, except the only integrals that you can compute without the substitution rule are the integrals that are on the antiderivative sheet. There's some tricks, like multiplying out or splitting up fractions and stuff like that that can make it seem like you're doing something more complicated, but without the substitution rule, the only antiderivatives you can do are the elementary ones, and then the elementary ones wearing a beard and glasses so that they look like they're not really just the basic antiderivatives. You have to do a little bit of algebra and understand exponents. Do you understand exponents? And so now we really start to be able to do some pretty cool stuff with the substitution rule, and if you've been watching all of these videos, you're like a hero, because it's been going on forever. But let's do a few. I couldn't possibly do enough because they're so important. You should be able to do all of them. Remember my rule about what is easy. So I would say 7 through 12 are easy. If you can't do all of 7 through 12 pretty easily, then you don't know enough. And if you can do all those easily, then you'll definitely get at least a B. I accidentally maximized that. Let's do some of these. Do these look easy? I know people have a hard time with these. One problem people have such a hard time with these is because people tend to be very weak at composition of functions, and the trick to doing these is to be able to see a composition, and a lot of people just haven't learned to do it. I'm just picking one at random, let's do number 12. So you can see there it is right there, and the substitution that makes this one work is u equals x squared plus 1, because in that case du is 2x dx, and then divide both sides by 2, and you get du over 2 equals x dx. And the advantage is now, do you see x dx is basically the numerator? So what happens is, taking that 1/2 factor into account, the numerator basically becomes du. And in the bottom you have u squared. Now, if only we had some kind of understanding of the way exponents work, we could easily do this. Unfortunately, it's virtually impossible to understand how exponential notation works. And, maybe we could invest thousands of hours in trying to learn how exponential notation works, but it's probably better just to ignore the fact that we have no idea how it operates and then hope for the best. So that's the best strategy, so that's what we're going to do. And this becomes minus 1, so got minus 1 over 2 times u. And now if we sort of undo, oh shoot, we accidentally used exponential notation. Now if we just undo the substitution, which was x squared plus 1, this is minus 1 over 2 times x squared plus 1. And you can take the derivative and verify that this is the right answer. So maybe instead of doing all of these, I'll just give you an idea of the substitution for some of these. Here the substitution is u equals 2 theta, because this is really similar to, just the derivative of secant. Here the substitution is pi times t. Here the substitution is 3ax plus b times x cubed. What else have we got? Here the substitution is x squared plus 1. Here the substitution is e to the x. Here the substitution is 3t plus 2. Here the substitution is x cubed plus 5. Here the substitution is 5 minus 3x. Here the substitution is 3x minus 2. So try to do all those. I know that you don't have all the time in the world, but so what about these? Here the substitution is natural log of x. Here the substitution is square root of x. Number 21 looks interesting. Let's do that. So I'll actually copy that one over. So we've got cosine root t over square root of t dt. And I've noticed there is always at least one student that sometimes tries to do crazy things like separate a trig function from its input. You guys know that cosine and square root of t are like married to each other, right? Because it's a composition of functions. And so this is as important to understand as the exponential rules. Let's try what I said was the substitution. Let's see if I'm right here. So we've got u equals that, and now du is 1/2 t to the minus 1/2 dt. And one thing that makes this problem a little tricky is not only do you have to know a little bit about exponential notation, which we've all, come to the consensus that we're going to completely ignore, you also need to do this little bit of algebra and need to get rid of this 2 to fix things up. So it becomes t du equals dt over the square root of t. And here is dt over the square root of t. And we've totally eliminated t now. This has just become, you've got this factor of 2, but other than that, this is just cosine u du. And so this is 2 sine u. And so it's 2 times sine square root of t plus c. It's the final answer. And, oops. What else have they got? Number 65 is kind of hard. I suggest you try that one. We did it in class. Here the substitution is e to the x plus 1. Here the substitution is pi over x. This is also a good one. I suggest you do number 34. What else have they got? Can you do number 37? Let's do number 37. I think that's a good problem too. What's going on here? Number 37. And the secret to number 37 is to know the definition of cotangent, which is cosine x over sine x dx. And now the substitution is u equals sine x, and du equals cosine x dx. So this is really just 1 over u du, which is natural log of u, which is natural log of sine x. plus c. That's it. That's number 37. For number 39, do you see it? Do I see it? What am I talking about here? Yeah, so the substitution is u equals tangent. Number 39 is great. Let's do that one. So we've got secant cubed x tan x dx. And let's do u equals tangent. Starting to get a little bit loopy. Du equals secant squared x dx. Are you writing these dx's? Are you writing anything at all? You need to write the dx. I've noticed in class and just, just human nature, people want to write as little as possible, but you have to be really precise. Every single thing has meaning. You have to write all the symbols. If you don't write dx, that's an easy way to make these things really hard for yourself. So do you see that this is secant cubed is the same thing as secant squared times secant? And here's a secant squared. So here we've secretly got a secant squared times dx, and that leaves over 1 secant. So you've got that, and oh crap, I made a mistake, didn't I? Shoot. Yeah. Well, haven't I said in class that sometimes things just go wrong? Yeah, that's the ticket. Sometimes things just go wrong. And I guess that's what happened to me right here. I made a mistake, so maybe I'm not as smart as I think I am. Maybe it's time to hang it up. Maybe I wasn't really cut out to be a mathematician. Secant cubed x tan x, not tax, tan x. Okay, so let's try not to biff it. Let's see if it helps to expand this. So this is the same thing as 1 over cosine cubed x, and now this is sine x over cosine x dx, and I think that's the secret, isn't it? Because now you've got sine x dx over cosine to the 4th x, and now just do u equals cosine x, and then du is minus sine x dx, and so you get minus du over u to the 4th. And now if only we decided to learn how exponents work, we would know that that's true. So this is minus, remember it goes up when it's negative. We're almost done. What was u? It was cosine minus cosine to the negative 3 x over negative 3 plus c. You can cancel those negative signs. And this is not cosine inverse, this is actual reciprocal of cosine. So maybe I should actually write it out nicely. So it would be 1 over cosine cubed x times 3 plus c. Great. Now I have to tell you, I'm kind of tired now. I don't know how much longer I can keep doing good work and making sense, or if I would at least maintain the level of sense making and goodness working that I've been managing until now. But I should do at least one of these with the limits. So pick one. I would pick number 61, but for number 61 we would need to know how exponents work. But I don't know, exponents are pretty tough. Sometimes a person's just got to know their limitations. Sometimes it stops at, I don't know, exponents. You can learn how to change the solenoid on a car, or like install Linux on your cell phone or something, but exponents are really, really hard. So what happens if we change if we actually undo this exponential notation for number 61, right, so this is the same thing as 1 plus 2x to the negative 2/3 power. It's not a very good d. And so let's do, once you get to be a real calculus wizard, you'll be able to do this without doing substitution. Du equals 2 dx, and so that means du over 2 is equal to dx. Now comes one of the things that we're supposed to be emphasizing here is how to change the limits. And I want to remind you that one advantage to changing the limits is that after we change the limits, we never have to go back to x again. So don't go back to x at the end of this problem like you normally do with the indefinite integral, because we're trying to get a number, and by changing the limits we can just compute that number with respect to u. We don't need to go back to x. That's not the right number. So as I've said many times in my Cassandra-ish pleading, to plug in 0 in for this number, and then you get 1 and plug 13 in. That gives you 27. Okay, and you've got this factor of 1/2 has to be written. And other than that, this has just become u to the minus 2/3, or at least that's what, you know, the people those eggheads whose job it is to understand exponents, that's what they tell us. And now it goes up to u to the 1/3 divided by 1/3, but I'm just going to multiply by 3. And I guess I'd better not write it. That 3 doesn't deserve to be in red. So it's the same as that. And now this is 3/2 1 plus 2x. Oh shoot, I went back to x. It's because I'm tired. Sorry. I forgot that we were doing the definite integral. So we're doing the definite integral. That means you just go from 1 to 27. And so this is 3/2. And the 27, the people who understand exponents tell us that 27 to the 1/3 power is the same thing as 3, because 27 is 3 cubed. And now if you take away, 1 to any power is just 1. Oh, that's pretty. The answer turns out to be 3. So, do all these. What have I told you to do? I've given you like 13 hours worth of work to do, I guess. But life is hard. Math is hard, man. I spent a lot of time studying math when I was in college. I'm going to stop the video, so I'm going to declare this to be the end of the review. Should I do that? Let's see what else they got down here. You guys didn't buy my bluff because you could see that there were more seconds left in the video. You know what, though? I think I was going to say that I'm just going to do what I said I was going to do. Oh my god. Look at number 85. Nobody could resist doing number 85. Certainly not me. So let's do number 85 together. Okay, so let's do number 85. Let's do number 85. Let's do number 85. I should be in an institution. Let's do number 85. And this is 1 minus x to the b dx. I haven't read the question, but I'm a recording and you can pause the video and read the question yourself. I'm supposed to prove that it's equal to that other thing. How do you do that? It must just be that it happens by magic if you do the substitution. Is that right? Then du is minus dx. And now let's try to fix everything up. So this is x to the a. And in this problem we're going to have to use the genius method, solving for u in terms of x. So here I need to express x in terms of u, and this equation is what I have to work with. So what I need to do is 1 minus u is equal to x. You can work that out yourself. It's just simple algebra. And that means that this x becomes 1 minus u to the a, and 1 minus x is u, so this gives u to the b, and I've got a minus sign here. Now, the minus sign is this minus sign, by the way. Now when the bottom limit is 0, this becomes 1, and when the top limit is 1, this becomes 0. But the negative sign lets us straighten all that out again and just go from 0 to 1. And let's write it as u to the b, 1 minus u, oh I forgot to write du, du to the a. And the only difference between what we have right now and this is that we're using the letter u instead of x. But the letter name doesn't make any difference, so let's just change the name of the letter back to x. Why don't we? And quad erat demonstratum, baby. I'm going to stop the video for real now.